So I was trying to figure out how many dogs are Labradors, and so I went out and I found this dog, and it was a Labrador, and I concluded that all dogs were Labradors, and I made this graph that I really want to show you guys about how all dogs are Labradors, and there was a mistake in the graph. Anyway, so then I was like, then I found another dog. What is that? And it wasn't a Labrador. That was what I knew it wasn't. So I was like, wow, I guess 50% of all dogs are Labradors. And then but there was this other dog walking down the street and it was totally a Labrador. And I was like, I guess 2 out of every 3 dogs are probably Labradors. And I was like, how many dogs are Labradors? Like, I should know. So I got a lot of dogs. Like, so many dogs. Like, I don't even know how many dogs I got. So many dogs. And I was like, the proportion of Labradors kept changing. It didn't settle down. I was like, I don't know how many dogs are Labradors. I just don't even know. And eventually I had like a million, like 35 samples. And I was like, what if it's still wrong? So what does right mean? Right means like if I took all the dogs in the whole world, I guess. Like all the dogs. And I put them like on a big line. Because I can do that because I'm a mathematician. I can put a bunch of dogs on a line, all the dogs in the universe. And then there'd be the proportion of dogs that were labs and the proportion of dogs that are not labs. And I could just count the number of labs and divide by the total number of dogs in the universe, right? But I can't count all the dogs. So I'm just going to pick a couple random dogs is what I'm doing, right? I'm just picking totally random dogs, and then I'm seeing of the dogs that I've picked so far, these like randomly selected dogs from this line that includes all the dogs in the universe, which proportion of them were labs, right? So that's like a random sample. Okay, but the problem with a random sampling is that you don't really, since it's random, you could get like all labs or you could get all not labs. Like each time you do this, you're going to get a different result, and like which result is like more accurate, like it's random, like anything could be happening. What? So in order to understand the accuracy of the proportion that we get after, say, 89 samples, we need to know what randomness is. Okay, randomness, that's like throwing darts, basically. Like all kinds of randomness, like whether it's like flipping a coin or like rolling die, they can all be thought of as like you're throwing darts at some kind of a space, okay? And the proportion of the space, the size of the space that's taken up by heads, that has to do with the probability that you're going to hit heads. So comparably, if we take a dartboard, well actually a dart line in this case, and we split it up into 6 equal parts, that's kind of like rolling die, right? You just throw darts down on this line and you can just, well, that's what rolling die is, right? And so just like you can roll die, you can roll anything, right? You can roll dogs. Well, you can't roll dogs. You can pick dogs randomly from the set of all dogs, right? That makes sense, okay? So basically, like I imagine that I have all the dogs in the universe and they're lined up on this line, and then I throw a dart and then I get a dog. Okay, and the probability that I get a Labrador, that's like the size of that space where all the Labradors are. Because I'm imagining that I've put all the Labradors on the left side of my magical line. Okay, that's pretty simple, but the kind of randomness we're dealing with is actually more complicated, because we're not just trying to pick one dog randomly, we're picking like lots of dogs randomly. So that's like a much more complicated kind of randomness, right? So what's that randomness like? Not just picking one thing at random, but picking many things at random. Let's try to think about what it would be to pick, for example, 2 dogs at random. So let's say we're going to try to estimate the proportion of dogs that are Labradors using only 2 dogs picked randomly. Okay, so like different things could happen. Like we could find like 2 dogs that were both Labradors, and we'd be like, all the dogs in the universe are Labradors. Or we could find like 2 dogs and neither of them Labradors, and we'd be like, no dogs in the universe are Labradors. Or we could find like 50-50, right? Different things could happen if we pick just 2 dogs randomly. So let's try to think about what it's like to pick 2 dogs at random. Okay, so it's kind of like picking 1 dog at random and then picking a dog at random from a bunch of clones of dogs. I know this seems more complicated, but actually it's going to make everything make total awesome sense. So we take all the dogs in the universe and we clone them, okay? And then we pick a dog and we pick a clone dog, okay? And sometimes we get a Labrador and a clone Labrador, and sometimes we get like 2 non-labs, okay? And so that's what picking 2 samples like. It's like throwing a dart, but instead of throwing a dart onto a line, you're throwing a dart onto like a real like dartboard, okay? And like the horizontal component kind of tells you like which dog you picked, and the vertical component kind of tells you which clone dog you picked. Okay, that's what picking 2 dogs is like. That's what randomness is when you have 2 samples. Okay, so what's the probability that we pick, say, like 2 labs? Well, okay, let's imagine that of the 575 million dogs on Earth, there are about 575 million dogs on Earth, that about 87 million of them are Labradors. Now, of course, if we really knew this, we wouldn't have to be doing this entire experiment. We're trying to figure out what percentage of dogs are Labradors, because we know that 87 million, which is about 15% of all dogs, are Labradors. So this would be totally stupid. But let's pretend that there were, in fact, 87 million Labradors, and then we were trying, somebody else was like, somebody who was stupid, who didn't know that there were 87 million Labradors, or was then trying to figure out what percentage of dogs are Labradors. Okay, but throwing down darts on a dartboard, which is 575 million long, is kind of hard to think about. So there's no reason we can rescale this line so that it was a little bit smaller. So the length of the line will be 1, and the length of the area with the Labradors will be about like 0.15. Okay, and the length of the area that not Labradors will be like 0.85, like, because we know that there's like 15% of all dogs are Labradors. Imagine, we're pretending. So you can kind of think of this like literally, like visually, like, okay, there's actually a line and it's a meter long, and the part of it that is the Labrador part of it is 0.15 meters, and the part of it that's not Labrador is like 0.85 meters. So then if you're actually throwing darts, the probability that you land in the Labrador part is like 15%. Okay, so now what if you're throwing darts on the labs and the clone dogs? Okay, what's the probability that you land in a region where you get 2 labs, right? Okay, so the size of the, for example, 2 lab region, it's a 15 by 15 box, right? Its area is 2.25%, which means that the probability that you land in that region is 2.25%, and likewise for all the boxes. Okay, so there's basically 3 possibilities, right? There's a possibility that you get 2 Labradors, or that you get no Labradors, or that you get 1 Labrador. Okay, but there's 2 ways you can get 1 Labrador. The real dog be a Labrador, or the clone dog be a Labrador. Okay, so it's like 72.25% probability that you get like no Labradors, because there's like 85% of dogs are not Labradors, and so the size of that square is an 85 by 85 square. Okay, and there's like 12.75 chance that you get like 1 Labrador and the other one's not a Labrador, but then there's another 12.75 chance that you get like not a Labrador and then a Labrador, and then finally there's like a 2.25 chance that you get like 2 Labradors. So what we just really learned is that if you use 2 samples to guess the proportion of dogs to Labradors, you're going to do a crappy job. You're either going to guess 0%, 50%, or 100%. So let's try 3 dogs. So, okay, so let's say we had 3 dogs. So if we're picking 3 dogs, that's like throwing darts into like a cake, like a big dog cake, where each point in the cake is a group of 3 dogs. So the horizontal component of the location of the dart tells you what the first dog was, and the vertical component tells you what the second dog was, and the depth component tells you what the third dog was, right? So this dart, the location of this single dart actually encodes for you a choice of 3 dogs. So in this case, you can see that because of the location of our dart, we picked like a Dalmatian and a Labrador puppy, it looks like, and some other kind of crazy dog, I don't really know. And because we picked those 3 dogs, if we were going to try to use those 3 dogs to estimate the proportion of dogs that are Labradors, we would estimate that 33% of all dogs are Labradors, because 1 out of the 3 dogs we picked were Labradors. Okay, so different things could happen, and you might want to know, like, what's the probability that we have different estimates, right? We could, depending on which random samples we get, we're going to get a different estimate of the proportion of dogs that are Labradors. And the probability that you're going to get some particular estimate, like say 1/3 or 66% or 100% or 0, you have to understand the size of these spaces in this dog cake, right? That's really the key object in any kind of a sampling process, is understanding the volume of those spaces. So now if we have like 35 samples, right, then you're no longer going to be throwing darts on a dart line or a dart board or a dart cake. You're throwing darts into some kind of a 35-dimensional hypercake. Okay, but even a 35-dimensional hypercake is not enough cake, because there's really an extra dimension, which is the proportion of dogs in the overall population, which are Labradors. If most dogs in the space were like this dog, then all of our probabilities would be different. We supposed that it was 15%. But actually we have no idea what the true percentage is. But fortunately, by adding just 1 dimension to our cake, we're going to be able to encode our uncertainty into that extra space and deal with everything right. Okay, so our first order of business is going to be finding some way to transform our hypercake down into some kind of low-dimensional space which still captures everything we're interested in. Only then, once we've reduced the dimension down to something that's sort of tractable, will we be able to add the 1 extra dimension which has to do with the true proportion of dogs in the overall space, which are Labradors. And then we'll be able to think clearly about what things really mean. If you take 35 samples and 7 of them are Labradors, what does that mean? What does that say? How can we think about that? We're going to use a technique called posterior analysis to find out, and we'll be joined in that quest by this dog, so I hope you're looking forward to it.